I'd like to introduce Thad Starner, who is the founder and director of Contextual Computing Group at Georgia Tech. He's also a strong advocate of wearable computing, as you can see, and has been involved with this since he did his PhD. So he's joined Google in 2010 and is the tech lead for Project Glass. So Thad?
Thank you. Well, thank you. So let me talk about the elephant in the room first of all, and get it out of the way. I cannot talk about glass per se. However, what I am going to talk about is a lot of the academic research that has been done in the past that's strongly influenced glass, as well as some personal experiences for the past 20 years. So if you have questions, I can answer them at the end based on those two topics. So let me get started and go right into displays. Because almost everybody who looks at wearable computers, for some reason, associates them with head-up displays, and that's because it's the most, well, in-your-face aspect of the devices, so to speak. Now, there are two types of heads-up displays. There are the type like glasses, which is, you can see through it. So, if you guys look at my eyeball right now, you can actually see my eyeball through the glass. But there's also the types that are opaque. For example, in the bottom image here are the displays I normally use. And I have that display with me. I can demo the academic system all you want later. And those are opaque systems. And people ask me, well, how can you wear that in front of your eyeball? Because that one, as you can see, I wear right here. And so we're going to do a quick experiment for those of you who haven't seen this before. Actually, do this experiment with me. It's kind of fun. So close one eye and take your thumb and move it until you're blocking my face. Okay, everybody got my face blocked? And now open up your other eye, and suddenly it seems like you can see through your thumb, right? And what's happening is your left eye, or your right eye, whichever one you picked, is filling in the vision behind what the other one can't see. And this works for 85% of the population. And it's one of the reasons you have two eyes is that you actually fill in this visual field pretty seamlessly. The other reason I want to do that experiment is now when I go back to Sergey and he asks me how does the talk go, I'll have everybody, just took a picture with glass, how about everybody doing this? And I can say, look, they love the talk. Okay. So you can actually get this see-through experience even when you have an opaque display. And I think that's an important thing to remember. Now, the other thing that people often get really excited about with these displays is they want a full field of view AR experience. And it turns out you really don't need that for a lot of things you really want to do with wearable computers. And keep that in mind as we go through this talk. And tell me after the talk of what applications you would actually think you need a full field of view binocular AR display. And I'd be happy to chat with you about that, because a lot of my friends who do AR can't give me anything convincing besides, say, augmented reality or military applications. Okay, for those of you who haven't seen me before, this is the Twiller. This is the keyboard I use. I type up to 130 words per minute on it. That's faster than many people on desktop keyboards. I sustain about 70 words per minute. And if you've seen a paper written by me or some email or something, it's generally written on this keyboard. And the Twiller also has a little mouse on the back side of it. And the Twiller 3, the Bluetooth version, is coming out shortly. I have the first prototype back in my lab right now. I'm trying to help them get some kinks out of it. If people are interested in that, I can give you demos later on. Now, most people associate wearable computers with these funky heads-up displays and these funky input devices. But really, that's not what we were focusing on. Wearable computing was designed, the field, was really trying to get on-body computers to support the user who's actually on the go. It's designed to be used while you're doing other tasks. And in many senses, it's been highly successful. I personally call MP3 players, mobile MP3 players, wearable computers. It's one of the first applications we designed, actually, was trying to do an MP3 player on a small device. And now they're ubiquitous. Health monitors is another thing we did early on. And that was with Ross Picard and Jennifer Healy. And that work really, you can see a lot of that reflected in industry right now. The whole quantified self movement is using wearable computers as part of people's daily lives to get some idea of wellness and health. And some of the stuff you saw in the early wearable computing conferences are now hard to think about not being here. For example, most of us use some version of Google Maps or some mapping software on our mobile phones. Most of us have used some short messaging service, some instant messenger. Most of us have actually done mobile email or content-based search. Some of you have probably downloaded an augmented reality application that uses your camera phone. And all these applications you could have seen at the first International Symposium of Wearable Computers back in 1997. And you could have seen that in the early 90s in the research labs at Georgia Tech, MIT, CMU, and Columbia. Now, what we've seen though is that cell phones have really taken off with these applications, and but it's really not what we were hoping for. The people in the wearable computing community was hoping for something that is much more subtle, something that blurs the line between the man and machine, doesn't show the seams as much. As Larry Page would say, currently there's too much time between intention and action with mobile phones. And I have a video here that fortunately was not made by me. It's actually a spoof done by the Canadian Broadcasting Company, Rick Mercer report. And I think it kind of shows what I think the failings of smartphones are.
Text, web, email, power in the palm of your hand for the professional on the go. And introducing the BlackBerry Helmet, reinforced polymer to protect the skull of the mobile professional on the go, with an antenna for better BlackBerry reception so you can spend more time on your BlackBerry. And a camera that broadcasts a picture of what's in front of you to your BlackBerry so you can always be looking at your BlackBerry. The BlackBerry Helmet with optional safety flag. Protect your skull while you destroy your thumb.
So what's really funny to me is not long after that spoof came out, somebody actually did an application for these phones that shows you the video from your front camera so you can walk. I mean, they have it actually on the app site so you can actually walk while looking at your smartphone. I'm not making this up. Go look at the iPhone App Store and the Android App Store. It's on one of those. Okay, so whoops, let me get back here. So I think that really, that video actually makes fun of these seams between man and machine, this sort of delay in being able to do things. And what we really took inspiration from was the term cyborg. Now, the press started calling, when we first started doing these wearable computers in the early 90s and we had enough of us wandering around the streets of Cambridge, the press started calling us cyborgs. I think the first Boston Globe article in '94 said, started calling us that, and we said, okay, we'll adopt that term because we can't avoid it. But if you actually look at the definition of cyborg, if you look at the original 1960 paper by Manfred Clynes and Nathaniel Klein, it talks about the seamless interaction between man and machine. And they were talking about putting men in space and how you're going to adapt the human body and the human intellect to handling the rigors of space. And if you talk to Clynes, he said that a good example of a cyborg is a man riding a bicycle. If you are riding your bicycle out on the street and a car cuts you off and you have to brake all of a sudden, you don't think about your hand grasping the brake grip, it pushing down, it stretching the cable, it transferring that energy back to the brake pads that crimp onto your bicycle wheel and stop you. No, you just stop. It's just part of you. And that's what we're trying to do with wearable computers. We're trying to make an intellectual augmentation so the way you think, the way you move, the way you look at the world is actually as automatic as braking that bicycle. And that we don't have on current smartphones. Now, I'm going to highlight some research at Carnegie Mellon by Dan Sorokin and Asim Smologic and Tom Martin from 1997. Because I think it really drove home a very specific task that showed the power of wearable computers in an industrial setting. So the Army inspects their tanks every time they come back from the field. And it requires two guys doing this. One will sit there with this 30-pound manual that's 1,000 pages. It has check sheets of what to look for. The second guy is the one who's crawling all over the tank, inspecting the tracks or the communication systems or the computers or the artillery or whatever else. And the guy with the book will yell out, make sure track is in groove, seated in groove 3 properly. And the guy inspecting the tank will go look at it and says, yes, it is slotted. And they keep on doing this back and forth. It's really inefficient. The other thing is that after, as the guy says, yes, it's slotted, the first guy will make a check box, or make a check in a box on his paper. And any notes he adds to it by hand. These notes at the end of the inspection would be transferred back to Army base and entered by hand, which causes, of course, lots of errors. So what CMU did is they made the ViewMan 3. This is a heads-up display. This is a private eye. Now, private eye has been around since 1989. It's really quite a nice display. It's a vibrating mirror and a column of LEDs, and it's quite clear, quite nice display. I still have one. They hooked this up to a computer in a big round case. It has a knob on it. That knob has some very nice feel to it. If you ever go out to CMU, grab one of these things. It's a very pleasant experience. And you select things by going click, 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 click. And you actually do the mouse click by pressing the thing down. And they've made this so it's very gross movement. You can put it into a lab coat, you can put it underneath your Army fatigues, and it just works. And the soldier would take the heads-up display and the system with the manual on it underneath the tank, through the tank, around the tank, and do the inspection that way. And what they found is that they got rid of that second guy. They got rid of that guy holding the book. So they reduced the personnel by half. They also discovered they reduced the amount of time taken to do the inspections by 70%. That includes all these errors that crept into the system later on because of the human transcription. So this is, I think, in my opinion, is one of the benchmark studies that showed, hey, look, wearable computers have a very, very powerful effect in these sort of situations. Another thing that's happening right now is, besides the tasks of inspection, maintenance, and repair, is order picking. Symbol made a system back in the mid-90s that was very good for order picking and for helping route packages at FedEx properly. Today, we're seeing order picking being a really big business for wearable computers. In particular, I was working on a project with University of Bremen and Daimler Benz for their factories. And this just came out in ISWIC 2012. The idea here is you have an assembly line for your cars, and each car coming down the assembly line is a little different. It's a different trim package, a different radio, these sorts of things. And you have all these parts coming in from suppliers all over the world. They're on these big shelves. And some part picker goes down the shelves, grabs the part, and puts it in a bin for that car. You're picking for 8 cars at a time. And the way this is done at hundreds of thousands of warehouses throughout the world is you get a physical printout of a paper printout with these 10-digit numbers that says what you need to pick. And you line up those 10-digit numbers with the numbers on the shelf to grab the right object. And of course, we're not very good at that. There's lots of errors that happen. But on an automobile assembly line, if you pick the wrong parts, and it goes to the assemblers. Remember, a lot of the stuff is by hand. You can't do it with robots because they don't have the dexterity. If you get the wrong parts to the assemblers, you have to stop the assembly line. And that's hundreds of thousands of dollars a minute that you're wasting. So the Daimler and a lot of these people do inventory warehouses. Over 50% of their cost is this human picking. They're very interested in making this more efficient and less error prone. And so let me actually show you the result of that, if I can. This is this wearable computing system. And for the purposes here, we're still using a paper system. A paper order comes out for the pickers. They scan it, and that tells the wearable computer to kick into gear. And the wearable computer will display onto the person's heads-up display where they are with respect to the shelves and which parts they need to pick on that shelf. It's all color-coded by shelf. And you can see the interface at the screen at the bottom of the video I'm going to play. So a new order comes in. This is Hannes Baumann, by the way. He's just finishing his PhD thesis on this. And notice down here, He's got to pick one from the blue shelf, left hand, one from the yellow, middle, two from the red, below middle, and one on the left, green. Notice if I try to do that in voice, it actually takes me longer to say it than it does for him to do it. And there's a scanner, a laser scanner, at the top of the shelves that it figures out which bin he's reaching into. So as he completes the action, it unhighlights that bin. The thing is also telling him which of, in this case, 3 cars he's picking for. Now this is the lab environment. I can't show you the actual Daimler environment, but this is designed to actually try different conditions for voice versus paper pick lists versus graphical stuff. And it turns out that when you do use the wearable computer, you virtually eliminate errors from the order picking, which saves you the cost of the equipment in the first year, easily. But also, if you do this, if you compare the wearable system to the paper-based system, the paper-based system takes 50% longer. Right? So the investment in this infrastructure is nothing compared to the benefit you get back from it. And like I said, there's hundreds of thousands of warehouses that do these pick tasks worldwide. Okay, now personally I find these things to be not the most compelling. I really want the wearable computer for me, right? I really want the wearable computer to change my lifestyle, change how I work. And so that's what I've been focusing on, and there's been groups at Georgia Tech and MIT and other places I've gone throughout the world where there's groups of people using wearable computers together in their real life to figure out how all this stuff should work. And one question you might ask is, what do we find compelling? Here is my list of compelling things, and I'm going to go through these quickly since I'm already running out of time. I see. Interesting that my clock here is different than the clock there. Mine's right. Mine's set to atomic time. Let's get in here. I'm going to talk about some of the funkier stuff first, the stuff that people in the audience might not have heard from me before. This is the augmented senses part of this. And Lenny Foner, one of my colleagues at MIT, did this in the mid-90s. And here's the idea of being able to hear color. He calls it synthetic synesthesia. The idea is that I put a spectrometer on the side of my head with a little laser pointer. And when I look at a color, it translates that visual spectrum into an audio spectrum that I hear. Because we hear many more frequencies than we see. And so when Lenny was scanning over an area, he can actually tell the difference between a leaf and a photocopied leaf, even though they look the same to the human eyeball. Now, this is what you kind of see here. You can actually see the difference, and you can hear that, as you go from one to another. And this is, I'm sorry this is such a bad image. This thing is actually made out of Legos, I kid you not. And so Lenny is doing a demonstration to the Army one day with this really weird headgear with colorful Lego blocks on it. And the Army said, hold it, you mean that if you scan over a scene, you can tell the difference between the actual leaves and the color of my camouflage? And Lenny said, well, yeah. The Army said, oh. Suddenly they were very interested in this work. But this is just one example of how you can do augmented senses. We see this now with far infrared, being able to see in the heat spectrum, being able to see in ultraviolet, being able to do virtual things like being able to see through walls using diagrams and head tracking. So this idea of augmented senses really gets people going. People find this very compelling. Another thing that has come out recently is this idea of passive haptic learning and passive haptic rehabilitation. Now, how many of you out there really would like to learn a musical instrument or try to learn a musical instrument in the past? And how many of you have actually given up? Right? Why have you given up?
It's too hard. I started too late.
Too hard, right. It takes all that time and effort to get that muscle memory. What if I told you I could give you a glove? At the end of this lecture, you'd know how to play Amazing Grace without paying attention to it, right? This is really wacky. So here's the actual idea. Suppose I download a song that I want to learn into my cell phone, and I wear a little Bluetooth headset. And on my hand, I wear a glove. And that glove has little vibrators on it that tap my finger. Now, as each note is played, it taps the finger that belongs to that note. And so you just have this thing on throughout your daily routine, and you actually learn the muscle memory of the song. I'm not saying anything about musicality, but you learn the muscle memory of the song. Now, let me actually show you, another thing I should add is that we've done this experiment 5 different times, in pretty formal settings, on 2 different continents with 3 different sets of grad students. As in science, when you have something that's a surprise, you don't believe it until you've replicated it a few times. And I really believe this in this research now. I really believe that there's an effect. I believe in it so much that we actually did it live on CNN. Do not do live TV demos. It's really nerve-wracking. So this is Chad Myers here on the right. He's a meteorologist for CNN. And he has no musical talent whatsoever. Really, really bad. And he was tracking a hurricane in the Gulf of Mexico the day we were there. And the segment before, we slapped on the glove and he said, well, what do I have to do? And we said, nothing. He said, what? No, it'll teach you how to play the song. And I will tell you that's really quite weird. I did this live at my Chi talk on the subject. I'd never been a subject before. I haven't played piano in 30 years. I was never very good at it. So I put on this glove, I did a Chi talk on this thing, and said, we're going to do this experiment. At the end of the talk, I'm going to try it. And it really is quite nervous. It really is quite frightening. You get in front of a room full of people like this, and you're sitting there, and you have no idea if this is going to work. And suddenly your hand becomes possessed, and it works. And you'll watch this guy, you'll watch Chad. Chad's been in front of 20 million people every day for his life for years, right? You'll watch him start to freak out during this segment as he doesn't think it's going to work.
How long now?
About 45 minutes.
About 45 minutes. What was the song?
Well, this is what the song would have sounded like.
Okay. That's the before.
That is my musical repertoire.
Okay.
That's how good I can do it.
So, he's had the glove on for 45
now-
minutes. And what was the song, by the way?
It's
de Joy.
It's
Ode
Beethoven's
Ode to Joy.
Oh, this ought to be good. All right, Chad.
Okay. This thing buzzed. and all I did was I played on my
Watch him
mouse.
start to play.
Okay.
I did my little
You were doing
hurricane
other
stuff.
things.
Did my hurricane stuff, and it was buzzing on my fingers.
You were working.
Let's see if I can do it.
Oh, you gotta be kidding me. Are you?
So, thank you. It's probably the simplest song anybody's ever gotten applause for. And if you watch the full segment, you can see he suddenly realizes it's going to work, and he gets better and better because this is his first active practice with the system, right? But we did this demo at Georgia Tech, and one of my colleagues, Debbie Bacchus from Shepherd Center, they do a lot of work with spinal cord injury, was there at the time and said, Thad, I really want this for our patients. I was like, why, Debbie? How can this possibly help you? She said, well, Thad, I work with people with quadriplegia due to partial spinal cord injury. And these people still have sensation and dexterity, but but they have clawed hands, right? They can still move, they can still type, but they don't have the sensation and dexterity that you and I would. And I think that your device might actually be able to help them. In particular, I'm worried about our patients 1 year post-injury. Because 1 year post-injury, the insurance benefits go away. All the conventional, a lot of the literature says that your rehabilitative effects become asymptotic about after a year. You don't get much benefit. And rehabilitation, as you probably all know, is very expensive. It's all this one-on-one mentoring. She's like, well, if we could actually get some effect from your glove, be minimal overhead, minimal expense, and we might actually be able to help these people's lives. And so we did that experiment. We had 10 people. This is something that just got done a couple months ago. We're writing it up now. We had 10 subjects, and this is Tanya's PhD thesis. And half of the subjects had 3 lessons a week of 30 minutes of active practice. The other half of the subjects had that, plus 2 hours a day, they had the songs on their hand, played every day, 2 hours a day. And what we found is the people who actually had that passive haptic rehabilitation, that glove on, they had significant improvements in their sensation on their hands. And I'm not talking, this is just a little marginal thing. I'm talking about they cross boundaries from being in danger of hurting themselves and not detecting it to actually having more normal sensation. You can see the PhD, you can download it and see the results. And even better yet, these people could grab and release objects faster. And we had some subjects in our pilot study who said, now I can button my own buttons, which is a huge deal, right? Being able to dress yourself. I can now feel the heat in a cup of coffee immediately instead of having to wait a few minutes. I can now feel the texture of my sheets, right? And and what's also really kind of fun is we had one subject who he was 70 years old, and when he realized that we were going to teach him how to play piano, he requested happy birthday. And so he wheeled into his grandson's birthday and played him happy birthday on the piano. And that was a big emotional impact for him. And so there's this motivation factor. This is not rehab. This is fun. This is learning a new skill. And so we're quite excited about this, and we're trying to tell everybody because we really believe there's a future in these passive haptic learning and passive haptic rehab devices. Okay, going forward, there's a lot of other things out there that's happening now. We did a lot of stuff on augmented memory, a lot of stuff on something called dual purpose speech. But since I'm running out of time, let me show you some fun stuff. This is by a colleague of mine, Tony Jabara, at Columbia.
If you want to be one of the best pool players in the world, but don't want to practice, not a problem. An idea right out of science fiction could one day help you play better than anybody on the planet. New York Bureau Chief and pool shark Rick Lockridge has tonight's Hot Click.
Sometimes what seems like science fiction is just waiting for a lucky break.
I was watching this show, Quantum Leap, and there's this holography thing that is helping the main character play pool. I said, we can build that.
So Tony Jabara of the Machine Learning Lab at Columbia University set out to design a laptop and lipstick camera rig that would calculate the shot with the best odds of success, line that shot up for you, and update itself 30 times per second.
They show you virtual lines on top of a pool table, just like that science fiction show.
But could it turn an average player into a sure enough hustler?
Can you see through the display?
League night at Brooklyn's Park Slope Billiards. Rack 'em up for some beta testing.
If you can practice enough to get that coordination down to where you're realizing you're using a real cue ball in a virtual world, sure, that'll be helpful.
At the beginning, I said...
Okay, you get the point. And one of the other things that we're seeing right now is a lot of stuff is gone out of the academic labs into real world. Let me see if I can find, whoops. My apologies, I don't seem to have it right now. Maybe it's this one. Nope, wrong one. Okay, the one I wanted to show you is up here. This is WordLens. It's an application you can download. It actually will, in real time, translate street signs from one language to another. Right? And this is now starting to get in the realm of useful. You can imagine instead of having it on your cell phone, having it on your eyepiece would significantly improve your ability to interact with things. Now, let me the few minutes I have left here, let me talk about some challenges and how you actually, and the stuff we've learned in doing wearable computing systems like this over the past few years. Number one is whenever you start a wearable computing project or ubiquitous computing project for that matter, you got to consider four main dimensions. One is privacy, one is interface, another is heat and power, and then finally is networking, both on and off body. You got to keep, and whenever you do a change in your design, you really need to keep these principles, these dimensions in your head. Any change to one causes changes to the other. And I cannot tell you, how many times I've considered something about privacy and had it change my heat profile, or vice versa. Another thing to consider is practicing privacy by design. If you've not seen this paper by Marklin Heinrich and you're doing work in this field, I highly recommend it. Another thing to do is to minimize attention. Finally, we should also encourage socially graceful use. Let me run through these things quickly. Privacy by design, please read the paper, it's very useful. Attention, Mark does a whole lot better job explaining it than I can in a few minutes. With attention, one of the things to realize is attention is your most valuable resource when people are on the go. More than anything else in the system, attention is it. And one of the things that we've concentrated on in my research group is micro-interactions. What things can you do that are so fast that you'll do them all the time? For example, checking the time on your watch. Right? That's something you can do in a second or two. And it's something you'll do all the time. You don't think about it, you just do it. What other interactions are there out there that can be micro-interactions? Another thing that should be considered is, can you make the interface, the act of physically getting to the device and navigating to the right spot to either input data or get out data, can you get that to be under 2 seconds? Anything above 2 seconds, you see an exponential drop in the usage of the device, of the interface. Finally, when people are actually on the go, they need to checkpoint their spot in the interface quickly. You should strive to make all your interactions to take 4 seconds or less. Finally, you should design ramping interfaces. Interfaces where you might get an alert, but then your interaction, you do something else to get more information, so that the initial bit of information the user can ignore if they're busy, if they're attending something else. But if they want more information, they can interact with the device and get more information and ramp up the amount of attention level. The problem with a lot of what we've concentrated on in the past in HCI is we've been dealing with desktop computers where all your attention is on that graphing program or on that spreadsheet. Now we're getting out into the real world where people by definition are splitting their attention, and we've got to design interfaces for that. We should also design wearable computers for socially graceful use, something where people know what you're doing. For example, this is taking a picture, right? It kind of makes sense that that's taking a picture. You all know that I was up to something, right? It's very good to have the people who are standing around you have some sort of mental model of what you're doing with your device. So trying to design interfaces that convey how they're being used while they're being used, I think, is an important point. Finally, I want to leave you with 3 thoughts about what wearable computers should do. Wearable computers should help the user pay attention to the real world as opposed to retreat from it. Wearable computers should mediate interruptions instead of adding to them. Wearable computers should augment the user's eyes, ears, mind, voice, instead of miring them in the virtual world. And let me thank my sponsors. A lot of them are up there, and my industrial folks. And if you have any questions, we have about 7 minutes.
I come from a systems networking background. Just curious whether in a world where wearable computers become pervasive, every person carries one of these, are there new challenges for the systems and networking community?
Oh, yeah. I mean, but a lot of them are hitting with the cell phones, right? I mean, you're already wearing a work computer. It's in your pocket. It's called a cell phone, right? But, and they're starting to actually sense your movement. For example, I think the iPhone has shake to shuffle, right? Unfortunately, it false triggers whenever you're walking. Suddenly the tune changes. But I mean, there's a lot of stuff about systems that has to relate with power and the network. For example, Sergey and Larry have a paper from 1998. It talks about how much, when will cell phones actually cache the entire internet, right? All the static content. And they argue that this would be more power efficient than trying to retrieve it over the network. And if you do the math, 1 bit retrieved over the wireless is equivalent to 10,000 bits of storage, retrieved from storage. And so they actually drew this line that said, here's the exponential for the increase in static content on the internet, and here's the exponential for flash increase. And the crossover happened last year, according to their prediction. So there's a lot of system stuff there. Yeah.
In the 80s, the Lisp machine was the Cadillac of computers for
Yep.
me.
Mm-hmm.
And it died, and we were all left with Wintel boxes.
Yep. Well,
And
you were.
I was. That's right.
I was making a Spark station.
I should have followed your path, but I was stuck with the Wintel box. Many of us were, and so there's sort of a cautionary tale there about trying to develop really nice computer equipment for a niche market.
Mm-hmm.
Do you have that concern here? How can we avoid that same failure mode?
Don't do niche applications. right? So notice my research is not, the stuff I do is everyday life. The repair, maintenance, inspection stuff, those are $100 million markets, easily. But if you look at a consumer level item, right? If you look at, say, think about the Palm Pilot, right? Palm Pilot was a little touch screen that didn't do very well for inventory control or maintenance or any of that stuff. But it sold millions upon millions, whereas the Telzon systems that were at the same time, sold thousands. And eventually, the Palm Pilots were adapted for the inventory control systems. So it's good to go horizontal instead of vertical.
How do you keep, though, the mobile device, the phones that we all carry,
Mm-hmm.
from becoming the Wintel boxes of your field?
Well, they already are the
They can do
Wintel boxes
hundreds
of
of
my field.
apps. They can do probably most of the apps that you're interested in.
But there's a
but
difference.
not as well.
But the thing is that it's a different form factor, and that changes things. For example, none of you are probably, some of you probably aren't even carrying laptops at this point. None of you are carrying desktops, right? Why would you ever buy a laptop? Well, because it does something different than your desktop. Why would you ever buy a tablet computer? Well, because it does something different than your laptop. Why would you ever buy a wearable computer? Because it does something you can't do on your smartphone, and that's this fast access stuff. Here, let's do it. Let's do a race. Take a picture.
You'll be able to do it better than me, but I'll be able to.
No,
be able to do a half-assed job of it.
Time's done. You didn't even get started.
Right?
My son's first steps already happened. Your phone's still in your pocket.
The machines are better than Wintel boxes.
Right. So that's the point. Having wearable computers, having that fast access time, is what fundamentally changes how you live with these devices.
Pat? So, hi.
Hey.
Hi. So there's this is a point you've probably looked at, but I'm curious because you've made this assertion that it's the thumb test,
Yep.
the let's show the picture to Sergey test. So right now you can see both of my pupils.
Mm-hmm.
And
you can see both of mine.
So the issue, because you'd made this thing about it's okay to cover the pupil.
No, I didn't say it's okay. I said it's what I was doing.
Oh, okay. So because it seems to me that those subtleties might actually make a big difference. Like if I see two pupils or one pupil when I'm having a social interaction with someone, this might have a big impact on how our brain processes what I'm socially doing with that person. Yeah. So you kind of moved over that quickly. So I'm curious, how much have you looked at that as an important?
Well, one of my colleagues at Georgia Tech has an active fashion line. I've now been in the Bullet, and I co-teach classes between CS and industrial design. It's really important, and I've had to learn that vocabulary and how to do these things. And I didn't for the longest time. Hmm?
So when you took that picture, we all knew you were doing that. One can imagine not too far in the distant future, where as storage and video get cheaper and more ubiquitous, that some people would choose just to continuously monitor all of their waking hours,
Yep.
audio and video, and have a record of that stored.
Mm-hmm.
What thoughts do you have about that in terms of what it means for privacy and what kind of norms might change? Is that something you thought about?
That's something, you notice that a lot of my talk was about privacy, but I don't have time to go into the technical details, right? There is the technical details, right? One thing about the record all the time thing is a phrase that Gordon Bell calls write once, read never, right? People capture, we have the ability to do this. And we did this project with the military at one point where we were capturing their foot patrols in Iraq. And he said it's not possible to gather too much data. So we rigged them all up with video and high resolution images, and we could tell what they're doing with their weapons. We could tell when they took a knee. We could tell all these interactions, and we captured all this and we got it and showed it to them. They said that's too much data, right? What they want is that little salient piece, and that's the hard part. And it turns out that
Yeah, but you capture everything, and then 2 days later you go back and say, wait a minute, what happened at that critical moment?
I
Now
have,
we have it.
except for Alzheimer's and the military. I'll stick for Alzheimer's and the military. I have not found a really compelling application for that sort of continuous recording yet.
Well, disaster recovery.
disaster recovery. That's still kind of paramilitary. So there's that aspect. The other thing is that we have had the ability to record everything we say in, I think, 4 gigabytes per year for decades. And this is something that Chris Smant talks about. And I think I got it right. It's either 2 gigs or 4 gigs. Okay. You know, we've been able to do that for a long time, and none of you are doing it right now. All of you could. All you've been able to do it for forever, but you're not doing it. And why is that? Right? It's just not useful to you. So there's the practical aspect. And there's the privacy side. So one of the reasons you guys don't do this right now is there's a social contract between me and you that when we're having a private conversation, you're not recording it. Or if you are, you're not going to share with anybody, and you're being smart enough about your security. Right? We're going to see that social contract change a little bit, but it's still the same social contract. Right? What I say here on camera is different than what I might say to you in person, and I expect a social contract of what you reveal to others. And that's still the same thing. It's between human to human. It's that social contract that helps protect privacy. But there's also all sorts of things about what you can do for the design of the device, making people aware of what you're doing. We can go through the principles later. I can give you some pointers.
Thank you, Thad.
Yep. Thank you very much, folks.